Internet Protocol provides the logic for routing data across global networks, but when a packet arrives at its destination subnet, that logical journey hits a hard boundary. An IP address cannot cross a physical wire. IP addresses are virtual constructs. They contain no mechanisms to interface directly with physical hardware, like a server's physical network interface controller. ARP operates as the strict mechanical bridge between OSI Layer 3 and Layer 2, translating a 32-bit IP address into a 48-bit MAC address. The host encapsulates the packet into a Layer 2 frame, so data can traverse the physical network. In the early days of the TCP/IP protocol suite, local networks were heavily fragmented. Administrators ran a competing mix of ChaosNet, DECnet, and early Ethernet. Attempting to maintain static, hard-coded maps of IP to MAC addresses in this environment was completely unsustainable, as hardware was constantly replaced or moved. In 1982, David C. Plummer authored RFC 826 to solve this. He engineered a dynamic resolution protocol that was entirely hardware independent. The simplicity of this dynamic mapping is what allows modern local networks to function at scale. But the unauthenticated logic designed for networks in 1982 is also the root cause of the modern enterprise's most critical local vulnerabilities. This schematic of an Ethernet frame shows exactly where ARP lives in the network stack. Unlike higher layer protocols that use port numbers or session IDs, ARP is a raw payload encapsulated directly inside a data link frame, identified by a specific ether type value of 0x0806. Looking closer at this payload grid, we see a highly structured fixed-length header. It parses instantly, reading the hardware type, the protocol type, and the sender and target addresses. Notice the hardware length and protocol length fields. By defining the size of the address dynamically, ARP can scale from a 48-bit Ethernet address to entirely different architectures, like ATM or AX25, without requiring a change to its core format. The resolution lifecycle strictly follows a request and reply loop. When a sender needs a physical address, it generates an ARP request. Because the destination MAC is unknown, the sender populates the target hardware address field with all zeros. This diagram illustrates the request phase. The sender encapsulates the packet and targets the Layer 2 broadcast MAC address. This forces every single connected device within the local subnet to receive and process the frame. Every device inspects the target IP inside the payload. If the IP does not match their own, the devices silently discard the packet to conserve processing power. Only the machine holding the requested IP responds. It generates an ARP reply, setting the operation code to 2, and fires it back as a targeted unicast frame. Because the original request included the sender's MAC address, the target knows exactly where to send the reply. The sender receives this physical address, logs it into its local ARP cache, and releases the queued data. This flood and learn cycle provides immense flexibility for network hardware. But performing a network-wide broadcast for every single packet would saturate the wire. The entire system relies on aggressive local caching, typically holding mappings for 15 to 20 minutes to avoid severe network latency. ARP operates under an absolute architectural constraint. It is strictly confined to the local broadcast domain. Our packets are never routed across a wide area network. To know whether a target is local or remote, the host calculates a binary AND operation, comparing the destination IP address against its own subnet mask. If that calculation reveals the target is on a remote subnet, the host alters its resolution strategy. It does not attempt to find the remote machine's MAC. Instead, it issues an ARP request for the physical MAC address of its default gateway. The local host delivers the frame to the router, which then strips the Layer 2 header and inspects the IP to determine the next hop. ARP acts strictly as a localized delivery mechanism, operating independently at every single segment of a data's global journey. Administrators have also adapted this architecture for specialized updates using Gratuitous ARP, or GARP. This is an unsolicited broadcast sent without a preceding request, primarily to force the network to update its mapping tables. GARP serves two essential enterprise functions. During the boot process, a host broadcasts its own IP to detect if another device is already using it, and during a high-availability server failover, the backup server fires a GARP to instantly rewrite the MAC address tables on the local switches, rerouting traffic without dropping connections. There is also Proxy ARP, where a local router intercepts a request and answers on behalf of a host located on a completely different subnet. The router provides its own MAC address, tricking the requesting host into believing the remote target is actually physically local. While GARP and Proxy ARP ensure connectivity during rapid failovers and transitions from legacy hardware, they generate high volumes of broadcast traffic. Relying heavily on Proxy ARP often masks underlying design flaws in the subnet architecture itself. The protocol's reliance on open broadcasts exposes a severe structural flaw. RFC 826 was drafted prior to the existence of adversarial network threats. The protocol is entirely stateless, with zero inherent mechanisms for authentication. Operating systems are programmed to inherently trust incoming ARP replies. They will accept and cache physical address mappings even if they never sent a request for them in the first place. This topology diagram demonstrates how an attacker exploits this trust to execute a man-in-the-middle or ARP poisoning attack. The attacker silently injects forged ARP replies to targets on the local network. The attacker poisons two caches simultaneously. They tell the victim host that the gateway's IP belongs to the attacker's MAC address. Then they tell the gateway that the victim's IP also belongs to the attacker's MAC. All traffic between the two nodes now physically routes through the attacker's machine. Mitigating this requires switches equipped with Dynamic ARP Inspection, a security feature that physically intercepts and compares packets against a trusted database of DHCP assignments, dropping forged replies before they reach the victim. Beyond hostile attacks, ARP's stateless design also creates severe routing instability in multi-homed Linux environments, a condition known as ARP Flux. By default, the Linux kernel assigns IP ownership to the entire host, rather than a specific physical interface. And if an ARP request arrives on interface A, the kernel might answer using the MAC address of interface B. This behavior shatters routing symmetry. Firewalls expecting traffic from a specific port will instantly drop the packets. Network engineers have to manually tune kernel-level parameters, setting ARP ignore and ARP amounts, forcing the server to behave deterministically. Because the core protocol operates on absolute trust, engineers must continuously deploy defensive filters on switches and kernel overrides on servers just to keep a local broadcast domain secure and functional. When network architectures scale to massive software-defined cloud models, the baseline flood and learn broadcast model becomes an immediate liability. A single ARP broadcast propagating across tens of thousands of virtual machines will instantly saturate switch CPUs. Modern data centers extend Layer 2 networks across global Layer 3 boundaries using overlay technologies like Virtual Extensible LAN, or VXLAN. In this diagram, we see how VXLAN prevents broadcast storms from destroying the wide area network. It implements a mechanism known as ARP suppression. When a virtual machine sends an ARP request, the local virtual tunnel endpoint intercepts it. Instead of flooding the network, the endpoint queries a local database, populated by a control plane protocol like BGP EVPN, and instantly replies to the host locally. By intercepting and answering broadcasts at the very edge of the virtual network, VXLAN proves that traditional ARP mechanics must be actively suppressed to achieve enterprise scalability. In highly optimized environments like the Amazon Virtual Private Cloud, traditional Ethernet-style ARP has been completely engineered out of existence. AWS uses the Nitro hypervisor to completely bypass local flood and learn mechanics in favor of a strictly software-defined approach. When an AWS instance issues an ARP request, the hypervisor catches the packet before it ever reaches a wire. It performs a lookup in an authenticated central infrastructure database, generates a response, and unicasts it directly back to the virtual machine. Because the hypervisor dictates all address resolution, local ARP spoofing becomes physically impossible. Furthermore, when an IP is moved between instances, the Nitro infrastructure automatically fires gratuitous ARPs to update all local tables in less than a millisecond, guaranteeing seamless IP mobility. The protocol has spent 4 decades transitioning from a rudimentary bridge for 10 megabit Ethernet mainframes to the backbone logic of global cloud fabrics. The physical execution has evolved from an open, trusting broadcast tool into a highly suppressed software function. But the necessity of translating logical routing intent into physical hardware execution, the exact mechanism detailed by David Plummer in 1982, remains the indispensable bedrock of modern digital infrastructure.